Deep in the cosmic microwave background, 13.8 billion years after the Big Bang, something terrifying is hiding in plain sight. Scientists have discovered a pattern that shouldn't exist, a direction in space that defies the most fundamental principle of modern cosmology. And what it reveals might mean that everything we think we know about the universe is catastrophically wrong. If you enjoy unraveling cosmic enigmas that keep physicists awake at night, hit that subscribe button, because what I'm about to reveal will make you question whether our universe is truly what we've been told. For over a century, cosmologists have built their models on one sacred assumption. The universe has no special directions, no cosmic up or down, no preferred axis around which everything rotates. This principle, called isotropy, is the bedrock of modern cosmology. Without it, Einstein's equations crumble. The Big Bang theory falls apart. Everything we've calculated about the universe's age, size, and fate becomes meaningless. But here's the problem. The universe doesn't seem to care about our assumptions. When scientists mapped the cosmic microwave background radiation with unprecedented precision, they found something that made their blood run cold. A pattern, an alignment, an axis stretching across the entire observable universe that points in one specific direction. They call it the axis of evil, not because it's malevolent, but because it evilly threatens to destroy the foundation of everything we thought we understood about reality. The discovery started innocently enough. The WMAP satellite spent years measuring tiny temperature fluctuations in the ancient light from the Big Bang. These fluctuations should be completely random, scattered across the sky like static on an old television. And for the most part, they are. But when researchers analyzed the larger scale patterns, something impossible emerged. The quadrupole and octupole moments, representing the biggest structures in the cosmic microwave background, weren't random at all. They were aligned, lined up, pointing in the same direction like compass needles, all orienting towards some cosmic north. The odds of this happening by chance? Astronomically small. We're talking about finding a specific grain of sand on every beach on Earth simultaneously. The implications are staggering. If the universe truly has a preferred direction, then our most fundamental theories are either incomplete or catastrophically wrong. The cosmological principle, which states that the universe looks the same in all directions, might be nothing more than a comforting fairy tale we tell ourselves. Kate Land and João Magejo, the researchers who first identified this anomaly, put it bluntly. Either this alignment is real and revolutionary, or there's something deeply wrong with how we're analyzing the data. Neither option is comforting, because if it's real, we need to rewrite cosmology from scratch. And if it's a systematic error that fooled some of the most sophisticated instruments ever built, what else might we be getting wrong? The scientific community initially hoped this was just a fluke, a statistical anomaly that would disappear with better data. So they built better telescopes. The Planck satellite launched with instruments far more sensitive than anything that came before. Scientists held their breath, hoping the axis of evil would vanish like morning fog under the light of scrutiny. It didn't. Planck confirmed it. The alignment was still there, perhaps even more pronounced than before. The universe, it seemed, was trying to tell us something. But what? Multiple theories have emerged, each more unsettling than the last. Some physicists suggest we might be living in a rotating universe, spinning slowly on some cosmic axis we've never detected. But this creates its own problems. A rotating universe should leave distinct signatures in the motion of galaxies, signatures we simply don't see. Others propose that our universe might have a preferred direction imprinted during the first fractions of a second after the Big Bang. Perhaps during cosmic inflation, when the universe expanded faster than light, something broke the symmetry that should have been preserved. This would mean inflation itself, one of our most successful theories, needs to be fundamentally revised. The most disturbing possibility is that we're not seeing the whole picture, that our observable universe, vast as it is with its 2 trillion galaxies, might just be a tiny bubble in something incomprehensibly larger. A multiverse where different regions have different properties, different laws, different directions. In this scenario, the axis of evil might be pointing toward the edge of our cosmic bubble, showing us where our universe interfaces with something beyond. Think about what this means. We've spent billions of dollars building telescopes, launching satellites, and collecting data about the cosmos. We've calculated the universe's age to within a few million years. We've measured its expansion rate, mapped its structure, and traced its history back to fractions of a second after its birth. And yet, staring us in the face is a pattern that suggests all of this might be happening within a framework we don't understand. The universe might have edges we can't see, directions that matter in ways we never anticipated, structures operating on scales that make our observable cosmos look like a single atom in a vast ocean. Some scientists argue this is much ado about nothing. They point out that statistical anomalies happen, that if you torture the data long enough, you'll find patterns that aren't really there. They suggest contamination from our own galaxy, foreground effects that create false alignments, or simply the fact that random distributions can sometimes look non-random. These are valid concerns. Science demands skepticism. But here's what keeps the controversy alive. The alignment persists across multiple independent analyses. It shows up in different datasets. It survives various attempts to explain it away with instrumental errors or foreground contamination. The axis of evil aligns eerily close to the ecliptic plane, the plane of Earth's orbit around the Sun. Some find this deeply suspicious, suggesting it must be a local effect, something to do with our solar system or galaxy, rather than a truly cosmic phenomenon. But others point out that this alignment might be coincidental, or that perhaps there's a physical reason why our solar system formed in a plane that aligns with a larger cosmic structure. We simply don't know. What we do know is that this anomaly won't go away. As telescopes have improved, the measurements have become more precise, but the mystery has only deepened. The universe stubbornly refuses to conform to our expectations of perfect isotropy. And that should terrify and excite us in equal measure. Because in science, anomalies are where breakthroughs hide. Newton's laws worked perfectly until Mercury's orbit refused to cooperate, leading Einstein to general relativity. Physics seemed complete until blackbody radiation didn't behave as expected, opening the door to quantum mechanics. The axis of evil might be our generation's Mercury orbit, our blackbody radiation problem, a crack in the foundation that, when properly understood, could reveal an entirely new framework for understanding reality. Consider the ramifications if this alignment is real and cosmic in origin. Our cosmological models would need massive overhauls. The equations we use to describe the universe's evolution, the calculations that predict its future, the theories that explain its past, all of them rest on the assumption of isotropy. Remove that assumption, and you have to rebuild everything from the ground up. Dark energy, the mysterious force accelerating the universe's expansion, might behave differently in different directions. Dark matter, the invisible scaffolding holding galaxies together, might be distributed asymmetrically across the cosmos. The cosmic web, that beautiful neural network-like structure of galaxy filaments, might have an underlying orientation we've missed. Even time itself might flow differently depending on which direction you're traveling through the universe. The implications cascade outward like ripples in a pond. If the universe has a preferred direction, does it also have a center, a location from which that axis originates? And if so, where is it? Are we near it or far from it? Does being in different locations in the universe mean experiencing different laws of physics? Could there be regions where stars form differently, where galaxies evolve along different paths, where life as we know it could never emerge? These aren't just academic questions. They touch on the deepest mysteries of existence. Why is our universe the way it is? Why do the laws of physics have the values they have? Why is there something rather than nothing? The cosmological principle was comforting because it suggested that we're not special, that our location in the universe is fundamentally the same as any other location, that the laws we discover here apply everywhere, every when. The axis of evil whispers that this might be wrong, that location might matter, that we might inhabit a universe far stranger and more structured than we ever imagined. Some researchers are exploring whether this alignment could be evidence of a cosmic collision. In the early universe, perhaps our bubble of space-time collided with another bubble, leaving a permanent scar in the cosmic microwave background. This scar would appear as an alignment, a directionality pointing toward the location of that ancient impact. If true, it would be direct evidence of other universes, other domains of existence beyond our own proof, that the multiverse isn't just mathematical speculation, but observable reality. Others wonder if we're seeing the signature of exotic physics from the first moments of creation, perhaps particles or fields that existed only during the Planck epoch, that brief instant when quantum mechanics and gravity merged into something we can barely theorize about. These primordial entities might have left an imprint, a directional bias that influenced how the universe expanded and evolved. Studying the axis of evil might give us a window into physics at energies we could never recreate in any laboratory, forces that shaped reality itself. The mystery deepens when you consider that the alignment seems to correlate with other anomalies. The universe's expansion appears slightly different when measured in different directions. Galaxy rotation speeds show subtle directional dependencies. Even the distribution of gamma-ray bursts, those catastrophic stellar explosions billions of light-years away, hints at asymmetries that shouldn't exist. Are these all related? Are we seeing multiple manifestations of the same underlying phenomenon? Or are we pattern matching, seeing connections where none exist because our brains are wired to find order in chaos? Here's what keeps me up at night. What if the universe isn't just asymmetric? What if it's actively structured in ways we can't perceive? Imagine the universe as a four-dimensional object, twisting and turning through dimensions we can't directly access. We, trapped in our three-dimensional slice of reality, would see only projections, shadows of the true structure. The axis of evil might be one of those shadows, a hint of geometry operating on scales and in dimensions beyond our direct experience. If this is true, then everything we think we know about space-time is incomplete. Not wrong exactly, but limited. Like a two-dimensional being trying to understand a sphere, by examining only the circle where it intersects their plane, we might be missing entire aspects of reality, dimensions of existence that would make our cosmological puzzles suddenly make sense. The scientific method demands that we follow the evidence wherever it leads, even if it leads to uncomfortable conclusions. even if it means admitting that our beautiful theories might be built on sand. The axis of evil forces us to confront the limits of our knowledge and the possibility that the universe is under no obligation to make sense to us. As we build the next generation of telescopes and satellites, the mystery might deepen or dissolve. Future observations could confirm that the alignment is even more significant than we currently measure, forcing a revolution in cosmology. Or they might reveal subtle systematic errors that explain away the anomaly, letting us breathe easier but leaving us wondering what we might be missing. But here's the thing. The universe has already shown us that it delights in surprises. Every time we think we have it figured out, it reveals another layer of complexity: quantum mechanics, relativity, dark matter, dark energy. Each discovery seemed impossible until it became undeniable. The axis of evil might be the next chapter in that story. A cosmic mystery that, once solved, will open doors we didn't know existed. Until then, we're left with an unsettling truth. The universe has a direction, an orientation, an axis that points somewhere towards something, for reasons we don't understand. And somewhere out there in the cosmic dark, the answer is waiting. The universe is trying to tell us something. The question is, are we ready to listen? To truly understand why the axis of evil shook cosmology to its core, we need to go back to the beginning. Not the beginning of the universe, but the beginning of our ability to see it. The cosmic microwave background wasn't always the detailed map we have today. For decades, it existed only in theory, a prediction waiting to be confirmed. When Arno Penzias and Robert Wilson accidentally discovered it in 1964, they weren't looking for the echo of creation. They were trying to eliminate annoying static from a radio antenna. That static, that cosmic hiss, turned out to be the oldest light in the universe, stretched and cooled by 13.8 billion years of expansion. It was everywhere, uniform, the same temperature in every direction, 2 within 1 part in 100,000. This uniformity became the strongest evidence for the Big Bang theory and the foundation of the cosmological principle. But uniformity, it turns out, can hide secrets. The early measurements were crude by modern standards. They could detect the average temperature, but not the tiny fluctuations that held the real story. It wasn't until the COPE satellite launched in 1989 that we got our first detailed look at these fluctuations. And they were beautiful. Tiny temperature differences, just millionths of a degree, spread across the sky like a cosmic fingerprint. These weren't just random variations. They were the seeds of everything. Regions slightly denser than average would grow through gravity, eventually forming the first stars, the first galaxies, the cosmic web we see today. The pattern in the cosmic microwave background is literally a baby picture of structure in the universe. Every galaxy, every star, every planet, including Earth, can trace its existence back to those microscopic fluctuations. The COPE results were revolutionary, earning its principal investigators the Nobel Prize. But COPE's resolution was limited. It could see the forest, but not the individual trees. The next generation of instruments would need to look deeper, with finer detail, to truly understand what those fluctuations meant. Enter WMAP, the Wilkinson Microwave Anisotropy Probe. Launched in 2001, WMAP was a technological marvel designed to map the cosmic microwave background with unprecedented precision. It would orbit not around Earth, but around a special point in space called L2, a gravitationally stable location where the Sun and Earth's gravity balance perfectly. From this vantage point, shielded from Earth's interference, WMAP would spend years staring at the ancient sky, collecting photons that had been traveling through space since before the first stars ignited. The data started flowing in, and cosmologists were ecstatic. WMAP was confirming their theories with remarkable accuracy. The universe's age, 13.7 billion years, its composition, 4% ordinary matter, 23% dark matter, 73% dark energy. The geometry of space, flat, extending infinitely in all directions, everything fit together like pieces of an elegant puzzle. The standard model of cosmology, lambda CDM, seemed unassailable. But then Kate Land and João Magejo started looking at the larger scale patterns. Most researchers focused on the small scale fluctuations because that's where most of the information is. The large scale patterns, represented mathematically as low order multiples, contained less data and were harder to analyze with statistical confidence. But Land and Magejo were persistent. They decomposed the cosmic microwave background into spherical harmonics, mathematical functions that describe patterns on a sphere. Think of it like analyzing music. Just as any sound can be broken down into different frequencies, any pattern on a sphere can be broken down into these harmonics. The quadrupole, the L equals 2 harmonic, represents the larger scale pattern with 4 regions alternating hot and cold. The octupole, L equals 3, shows 8 regions. These should be oriented randomly with respect to each other. There's no physical reason for them to align. It would be like flipping 2 coins and having them both land on edge, pointing in the same direction. Yet that's exactly what Land and Magejo found. The quadrupole and octupole were aligned, not perfectly, but far more than random chance would allow. When they published their results in 2005, they called it troubling and suggested it might indicate new physics. The cosmology community's reaction was swift and divided. Some dismissed it immediately as a statistical fluke or an artifact of data processing. Others were intrigued but cautious, wanting independent confirmation. A few were genuinely alarmed, recognizing that if real, this alignment threatened the entire theoretical structure of modern cosmology. The controversy intensified when other researchers started finding additional anomalies, the so-called cold spot, an unusually large cold region in the southern celestial hemisphere that was far bigger and colder than the standard model predicted. Asymmetries in power between the northern and southern hemispheres. Unexpected correlations between the cosmic microwave background and the distribution of nearby matter. Each anomaly individually might be explainable. Together, they suggested something systematic was going on. The skeptics had valid arguments. The cosmic microwave background isn't pure. It's contaminated by foreground emission from our own galaxy, from dust and gas clouds, from synchrotron radiation produced by electrons spiraling in magnetic fields. Removing these foreground effects requires sophisticated modeling, and if that modeling is imperfect, it could create false patterns. The alignment with the ecliptic plane was particularly suspicious. If something about our solar system or our galaxy was creating a systematic error, it might naturally align with the ecliptic, since that's the plane where most of the solar system's matter orbits. Multiple research groups spent years trying to debunk the axis of evil. They used different data processing techniques. They applied various methods to remove foreground contamination. They looked for instrumental artifacts that might create false alignments. Some claimed to have explained it away. Others found the alignment persisted no matter what they did. The scientific literature became a battlefield of papers and counterpapers, each side marshalling evidence for their position. Then came Planck. The European Space Agency's Planck satellite was the ultimate cosmic microwave background observatory. Launched in 2009, it had better sensitivity, better resolution, and better calibration than any previous mission. If the axis of evil was an artifact, Planck would expose it. If it was real, Planck would confirm it beyond doubt. The cosmology community waited anxiously for years as Planck collected data and the analysis teams worked through the massive dataset. The first Planck results came in 2013. The cosmic microwave background map was stunning, the most detailed portrait of the early universe ever created, and the anomalies, still there. The quadrupole-octopole alignment, the hemispherical asymmetry, the cold spot. Planck confirmed them all. In fact, some appeared even more statistically significant in the Planck data than in WMAP. The Planck team was careful in their interpretation. They noted the anomalies and described them in detail, but stopped short of claiming they proved the cosmological principle was wrong. The team pointed out that when you look at enough statistical measures, some will appear anomalous just by chance. They emphasized that the anomalies were only significant at the 2 to 3 sigma level, meaning there was still a small but non-negligible probability they could arise from random fluctuations, but they couldn't make them go away. Here's what makes this so maddening for cosmologists. The standard model of cosmology is incredibly successful. It explains vast amounts of data with remarkable precision. The predictions of Big Bang nucleosynthesis, the formation of light elements in the first minutes of the universe, match observations perfectly. The growth of structure over billions of years, from tiny fluctuations to massive galaxy clusters, follows exactly what the models predict. The acceleration of the universe's expansion, the existence of dark matter, the flat geometry of space, everything fits. Except for these large-scale anomalies, it's like building a perfect watch that keeps time flawlessly, only to discover that the hands occasionally point in impossible directions. The watch works, but something is fundamentally not right. When confronted with observations that don't fit theory, scientists have 3 options: modify the theory, question the observations, or accept that we're missing something fundamental. Let's explore the theoretical frameworks that attempt to explain the axis of evil, each with profound implications for our understanding of reality. The first and most conservative approach is to assume the anomalies are statistical flukes. The cosmic microwave background gives us exactly one universe to observe. We can't run the Big Bang again with different initial conditions to see if the alignment was just chance. This is called cosmic variance, and it's a fundamental limitation of cosmology. We have a sample size of 1. When you analyze one dataset in many different ways, you'll inevitably find some patterns that look unusual. This is the multiple comparisons problem. Familiar to anyone who works with statistics, if you measure enough things, something will appear significant just by accident. Proponents of this view calculate that if you define unusual loosely enough, finding patterns at the 2 to 3 sigma level isn't that surprising. They argue that researchers went looking for anomalies and found some, but that doesn't mean those anomalies are real physical phenomena. It's like asking someone to think of a number between 1 and 1,000,000, and if they pick 372,491, being amazed at the coincidence because that's exactly the number you were thinking of. You weren't thinking of any specific number until they picked one. Similarly, the axis of evil might just be cosmologists finding patterns in noise and assigning them significance after the fact. This is a reasonable position, but it has a problem. Independent researchers using different methods keep finding the same alignment. At some point, repeatedly finding the same fluke starts to look less like chance and more like reality trying to tell us something. The second theoretical approach involves modified gravity theories. Einstein's general relativity has passed every test we've thrown at it, from the precession of Mercury's orbit to the detection of gravitational waves. But we've never tested it on the scale of the entire observable universe. What if gravity behaves slightly differently on cosmic scales? Some theories, like modified Newtonian dynamics, suggest that gravity's strength changes in extremely weak gravitational fields. This was originally proposed to explain galaxy rotation curves without invoking dark matter. But could modified gravity also explain large-scale anomalies in the cosmic microwave background? Perhaps the universe's expansion isn't perfectly uniform, because gravity itself has directional dependencies we haven't detected. This would be revolutionary, requiring us to extend or replace general relativity with something more complex. The equations would need additional terms, new fields, or higher dimensional effects that only become apparent on the larger scales. Several research groups have explored this possibility, developing models where gravity couples to additional scalar or vector fields that could impart a preferred direction. These models face significant challenges. They need to explain the axis of evil, while still matching all the other observations where general relativity works perfectly. That's a narrow tightrope to walk. Most attempts either fail to explain the anomalies or create new conflicts with other data. But the search continues because if successful, it would be the most important modification to physics since quantum mechanics. A third approach considers topology. We usually assume the universe is infinite and simply connected, meaning if you travel far enough in any direction, you keep going forever into new space. But mathematically, other topologies are possible. The universe could be finite and wrap around on itself, like the surface of a sphere or a torus. Imagine living on a giant cosmic donut. Travel far enough in one direction, and you'd eventually return to where you started from the opposite direction. Certain topologies could create patterns in the cosmic microwave background that mimic the axis of evil. If the universe wraps around on a scale just slightly larger than the observable universe, we might see correlations in opposite directions of the sky, because we're actually seeing the same structures from different angles. This is a beautiful idea that's been explored extensively. Researchers have searched for circles in the sky, matching patterns in different directions that would indicate cosmic wraparound. So far, no convincing evidence has been found. The universe, if it has exotic topology, seems to do it on scales larger than we can currently detect, but the search continues with each new dataset. The implications would be profound. A finite universe with boundary conditions would require completely rethinking cosmic origins and fate. Perhaps the most radical theoretical framework involves primordial anisotropy. What if the universe didn't start out perfectly uniform? The standard inflationary model assumes inflation smoothed out any initial directional bias, leaving us with a nearly perfect isotropic universe. But what if inflation didn't completely erase initial conditions? What if the inflaton field, the hypothetical field driving inflation, had directional properties? Some models propose that inflation itself could have been anisotropic, expanding faster in some directions than others. This would leave an imprint on the cosmic microwave background as a preferred direction. The challenge is explaining why inflation would be directional. Most models of inflation are designed specifically to create isotropy. Making inflation anisotropic requires adding complexity, additional fields, or potentials that break the symmetry. And then you have to explain why we don't see even more dramatic directional effects throughout cosmic history. Other researchers explore whether the axis of evil points to pre-inflationary physics. Perhaps in the first 10 to the minus 43 seconds, the Planck epoch when quantum gravity reigned, the universe had structure or properties that inflation couldn't completely erase. We have almost no understanding of physics at those energies and timescales. The marriage of quantum mechanics and general relativity breaks down string theory, loop quantum gravity, and other approaches to quantum gravity might predict relic effects from that era. The axis of evil could be a fossil, a faint scar from the universe's moment of creation, when the laws of physics as we know them didn't yet exist. This is speculative, but it's testable in principle. Different quantum gravity theories make different predictions about what kinds of relics they'd leave behind. Then, there's the multiverse hypothesis. If our universe is one bubble in an infinite foam of universes, each with potentially different properties, then isotropy might only be approximate, near the boundaries between universes, or in regions where our bubble nucleated from a parent vacuum. We might see directional effects. The axis of evil could point toward another universe, a neighboring bubble that gravitationally interacts with ours in ways too subtle to detect, except in the cosmic microwave background. This idea connects to eternal inflation theory, where inflation never completely ends but creates pocket universes continuously. In this scenario, our observable universe is a tiny patch in an infinitely inflating multiverse. The large-scale structure of that multiverse could imprint patterns on our sky. Some versions of this theory predict that we might see evidence of cosmic collisions, places where our universe bumped into another. During its early expansion, research groups have searched for such collision signatures, looking for specific patterns that would indicate an impact from another bubble universe. Another exotic possibility involves extra dimensions. String theory requires additional spatial dimensions beyond the three we experience. These extra dimensions are usually assumed to be compactified, curled up so tightly we can't detect them. But what if they're not? What if extra dimensions extend on cosmic scales, and we're simply confined to a three-dimensional brain floating in higher dimensional space? The geometry of those extra dimensions could create apparent directional effects in our three-dimensional slice of reality. Imagine living on a curved surface embedded in three-dimensional space. You'd experience your 2D world as having strange geometric properties you couldn't fully explain with 2D physics alone. Similarly, we might be seeing shadows or projections of higher dimensional structure that manifest as the axis of evil. Some of the most intriguing work involves studying whether the anomalies correlate with dark energy or dark matter distributions. If dark energy, the mysterious force accelerating cosmic expansion, isn't perfectly uniform, it might have preferred directions. This would revolutionize our understanding of dark energy, which is usually modeled as a cosmological constant, perfectly smooth and directionless. But what if dark energy is actually a field that varies in space, stronger in some directions than others? This could explain both the axis of evil and potentially other mysteries about cosmic acceleration. Similarly, if dark matter has large-scale streaming motions or anisotropic distributions that we haven't detected through galaxy surveys, this might show up in the cosmic microwave background. The quantum mechanics of the early universe provides yet another theoretical avenue. In the first fractions of a second, quantum fluctuations were amplified by inflation to cosmic scales, becoming the seeds of structure. But quantum mechanics is inherently probabilistic. Different outcomes occur with different probabilities, and we observe just one realization. Some researchers propose that the axis of evil might indicate we live in an unusual quantum branch, a low probability but not impossible configuration of the quantum initial conditions. This doesn't violate any laws of physics. It just means we're in the tail of the probability distribution. The anthropic principle might even favor such unusual configurations if they're necessary for the formation of complex structures like galaxies and life. Beyond the axis of evil, there are other observations that make cosmologists uncomfortable. Anomalies that don't get discussed much in public because they don't fit neatly into our theoretical frameworks. Let's explore these forbidden topics, the data that challenges everything we think we know. The hemispherical asymmetry is one such skeleton in cosmology's closet. When you divide the sky into two hemispheres, the cosmic microwave background should have approximately equal power in both halves. It doesn't one hemisphere consistently show stronger fluctuations than the other, and this asymmetry is statistically significant across multiple analyses and datasets. The difference is small, only about 7%, but it shouldn't exist at all in a truly isotropic universe. And mysteriously, the axis of this asymmetry aligns closely with the axis of evil. The coincidence is disturbing. Finding one anomaly might be chance. Finding multiple anomalies that align with each other suggests systematic physics we don't understand. The cold spot deepens the mystery. Located in the constellation Eridanus, this region is about 70 microkelvin colder than the average cosmic microwave background temperature and spans about 5 degrees across the sky. That's huge. Statistical analyses suggest that a cold spot this large and this cold should occur with a probability of less than 1%. Some researchers have proposed it's caused by a supervoid, an enormous underdense region in the foreground that causes photons to lose energy as they traverse it. But when astronomers mapped the matter distribution toward the cold spot, they found voids that are too small to explain its properties. The cold spot remains unexplained, an icy scar on the cosmic microwave background that defies standard cosmological predictions. Then there's the alignment of quasar polarization vectors. Quasars, the brilliant cores of active galaxies powered by supermassive black holes, emit polarized light. In 2014, astronomers studying quasars found that their polarization axes were aligned over distances of billions of light years. This is impossible according to the cosmological principle. These quasars are causally disconnected. They've never been in contact even at the speed of light, so there's no way for them to know how to align with each other. Yet the alignment is there, spanning scales of over 1 billion light years. The researchers who discovered this were cautious, noting that systematic errors could be at play. But independent analyses have confirmed the effect something is correlating quasar spins across vast cosmic distances. The cosmic web itself shows unexpected properties. When researchers map the filaments connecting galaxy clusters, they find that the orientations of these filaments seem to have preferred directions on the larger scales. The universe's neural network-like structure isn't as random as it should be. Some filaments align with others across hundreds of millions of light years, creating patterns that are difficult to explain with standard structure formation theory. Dark matter, simulations starting from random initial conditions, don't reproduce these large-scale alignments. The galaxy rotation problem extends the mystery. Galaxies in clusters should have random orientations, but studies have found that galaxy spin axes show subtle but significant alignments, especially for spiral galaxies. They tend to point in similar directions within large-scale structures, as if the cosmic web's geometry influences how galaxies rotate. This hints at angular momentum transfer on cosmic scales, a phenomenon not predicted by standard models. Even more controversial are claims about variations in fundamental constants. Some researchers analyzing quasar absorption spectra have suggested that the fine structure constant, a fundamental number governing electromagnetic interactions, might vary slightly across the sky. If true, this would be revolutionary. Fundamental constants are supposed to be constant everywhere, and everywhen variations would indicate that the laws of physics themselves change with location or direction. These claims remain hotly disputed, with other research groups unable to reproduce the results or attributing them to systematic errors. But the possibility alone is enough to give physicists nightmares. What if the universe isn't just anisotropic in its structure, but in its very laws? The Hubble tension adds another layer of confusion. The Hubble constant measures how fast the universe is expanding. When we measure it using the cosmic microwave background and working forward through time, we get one value. When we measure it using supernovae and other local distance indicators, working backward through time, we get a different value. The discrepancy is about 9%, far larger than measurement uncertainties. This shouldn't happen. It suggests either something is wrong with one or both measurement methods, or the universe's expansion rate has changed in unexpected ways. Some researchers have proposed that directional dark energy or anisotropic expansion could contribute to the Hubble tension. If the universe is expanding faster in some directions than others, and we happen to be measuring in a direction that's expanding anomalously, this could explain the discrepancy. The matter-power spectrum on large scales shows another peculiarity. The distribution of galaxies across the universe can be described by a power spectrum, essentially measuring how clustered matter is at different scales. On small scales, the observations match theory beautifully. On very large scales, approaching the size of the observable universe, there seems to be less power than predicted. The universe is smoother on the larger scales than it should be. This is called the missing large-scale power problem, and it's been nagging at cosmologists for years. Various explanations have been proposed, from exotic early universe physics to observational biases, but none are entirely satisfying. There's also the problem of the low quadrupole. The quadrupole, that larger scale pattern in the cosmic microwave background, isn't just aligned anomalously. It's also weaker than theoretical predictions suggest. The universe has less temperature variation on the larger scales than the standard model expects. This could indicate that the universe is finite, smaller than we thought, or that something suppressed fluctuations on scales larger than a certain size. Or it might suggest that our observable universe is embedded in something larger, with properties that dampen large-scale variations. The lithium problem compounds cosmological confusion. Big Bang nucleosynthesis predicts how much lithium should have been created in the first minutes of the universe. When astronomers measure lithium in the oldest stars, they find only about a third of what theory predicts. This is a factor of 3 discrepancy, far too large to ignore. Various solutions have been proposed, from exotic particle physics in the early universe to processes that destroy lithium in stars. But decades after its discovery, the lithium problem remains unsolved, a fundamental mismatch between observation and theory. Even the cosmic microwave background's temperature itself is slightly puzzling. Different measurement methods give slightly different values for the average temperature. The differences are small but persistent. More troubling, when researchers analyze the cosmic microwave background in different directions, they find hints that the temperature might vary very slightly with direction beyond what the dipole from our motion explains. If real, this would be another manifestation of cosmic anisotropy, suggesting the universe had different temperatures in different directions in the past. Some of the most exotic data comes from gamma-ray bursts. These catastrophic explosions, likely from collapsing massive stars or merging neutron stars, can be seen across billions of light years When researchers plot the directions of gamma ray bursts on the sky, they should be uniformly distributed. Several studies have claimed they're not. There appear to be preferred directions, clustering that exceeds random expectations. This is controversial and not universally accepted, but if true, it would suggest that even the most violent explosions in the universe are influenced by large-scale directional effects. The cosmic radio background shows anomalies too. Radio waves from distant galaxies create a faint glow across the sky. Recent measurements suggest this background might have directional variations that don't correspond to known source distributions. Something is making the universe brighter in radio waves in certain directions, and we don't know what. Could it be related to the axis of evil? Are all these anomalies connected, different manifestations of the same underlying asymmetry? Or are we falling into the trap of seeing patterns where none exist, connecting dots that are actually unrelated? This is the central challenge facing cosmology. We have a beautiful theory that explains most observations, but we also have a collection of anomalies, each small enough to potentially dismiss, but collectively suggesting something is off. Do we trust the theory and assume the anomalies will be explained away? Or do we trust the observations and accept that our theory needs fundamental revision? If the universe truly has a preferred direction, the philosophical implications are staggering. For centuries, humanity has been on a journey of cosmic demotion. We're not at the center of the solar system. Our sun isn't special. Our galaxy is one of trillions. Even our universe might be one bubble in an infinite multiverse. The cosmological principle was the culmination of this humility, stating that our location in space and time is utterly unremarkable. The axis of evil threatens to reverse this trend. If the universe has structure and directionality, then location matters. Our position relative to that axis matters. We might not be at the center, but we're somewhere specific in a universe that has geography, orientation, and potentially boundaries. Consider what this means for the anthropic principle. This philosophical position argues that we observe certain properties of the universe because those properties are necessary for observers like us to exist. If the universe were much different, life couldn't emerge. So it's not surprising we find ourselves in a life-friendly universe. But if the universe has directions and our location matters, the anthropic principle becomes more powerful and more disturbing. Perhaps observers can only emerge in certain regions or orientations within the cosmic structure. Perhaps the physical laws vary slightly with position, and we're in a rare pocket where conditions allow complexity and consciousness. This would make our existence even more improbable and precious than we already knew. We wouldn't just be lucky to be in a life-friendly universe. We'd be lucky to be in the right part of that universe, the part where the laws and conditions permit stars, planets, and life. The axis of evil raises questions about whether we live in a simulation. This is uncomfortable territory for many scientists, but it's worth considering. If we discovered that the universe has directional properties, edge effects, or systematic patterns that don't arise naturally from physics, it might suggest underlying computational structure. A simulated universe might naturally have preferred axes related to how the simulation is set up or computed. Grid artifacts, boundary conditions, or optimization choices made by simulators could manifest as the kinds of large-scale patterns we're observing. Before dismissing this as science fiction, remember that we already accept the universe operates on fundamentally discrete quantum principles rather than perfectly continuous classical physics. The leap to computational substrate isn't as large as it once seemed. If reality is directional, it affects our search for extraterrestrial intelligence. Perhaps life emerges preferentially in certain regions or orientations within the cosmic structure. If physical conditions vary with direction or location, then habitability isn't uniformly distributed across the cosmos. We might need to focus SETI efforts on regions aligned with whatever axis defines cosmic structure, or perhaps civilizations that arise in different orientations, develop different physics, or different understandings of reality based on what they can observe from their vantage point. Communication between civilizations in different cosmic orientations might face fundamental challenges beyond just distance and time. We might not just be separated by space, but by differing experiences of physical law itself. The implications for space travel are profound. If the universe has preferred directions, then travel in different directions might face different challenges or even different physical limitations. The speed of light is supposed to be constant, but in an anisotropic universe, could it vary with direction? Could space-time be easier to traverse along certain axes than others? Advanced civilizations might exploit these directional properties, traveling along cosmic grain, where physics is more favorable. Our current understanding of interstellar travel assumes isotropy. We calculate travel times and energy requirements based on uniform space-time. If that assumption is wrong, all those calculations need revision. Some directions might be accessible that we currently consider impossible, while others might be harder than we think. Think about the ultimate fate of the universe in an anisotropic cosmos. Standard cosmology predicts several possible fates: eternal expansion and heat death, eventual recollapse in a big crunch, or a big rip, where expansion accelerates until it tears apart even atoms. But these predictions assume isotropy. In a directional universe, different regions might meet different fates. The universe could expand forever in some directions, while recontracting in others. It could fragment into separate domains that lose causal contact. The long-term evolution might be far more complex and strange than our simple models suggest. Trillions of years from now, if civilizations still exist, they might inhabit a cosmos so directionally structured that different orientations might as well be different universes. The existence of a cosmic axis forces us to confront fine-tuning more directly. The universe appears finely tuned for life in multiple ways. The strength of gravity, the masses of fundamental particles, the ratio of matter to antimatter, the smoothness of the early universe. All these parameters seem precisely calibrated to allow complexity. The cosmological principle let us avoid some fine-tuning concerns by arguing that the universe is the same everywhere, so we don't need special explanations for our location. But in an anisotropic universe, we're back to explaining why we find ourselves in a region with the right properties for life. This might push us toward multiverse theories, where countless universes or regions exist with different properties, and we're inevitably in one that allows observers. Or it might suggest design, intentionality, structure imposed from outside the physical system. The religious and spiritual implications are impossible to ignore, though science alone can't address them. Throughout history, humans have sought meaning in the cosmos, looking for signs of purpose or design. The cosmological principles seem to remove any special cosmic significance. We're just here, in a random location, in a random universe, the product of impersonal physical laws and chance. But a universe with direction, with structure, with properties that depend on location feels different. It's easier to imagine intent behind a structured universe than a perfectly random one. This doesn't prove anything theological, but it changes the philosophical landscape. If the universe has design elements, we're confronted again with the question of design's origin. From a practical standpoint, if we're wrong about cosmic isotropy, what else might we be wrong about? Our measurements of the universe's age depend on assuming isotropic expansion. The calculated distances to far galaxies depend on isotropic cosmological models. The inferred amounts of dark matter and dark energy depend on assuming the universe is the same in all directions. If that's wrong, all those numbers need recalculation. The universe might be older or younger than we think. Distances might be systematically wrong in certain directions. Dark energy might be weaker or stronger than current estimates. The entire cosmic distance ladder, built up painstakingly through multiple overlapping measurement techniques, might have systematic errors we haven't accounted for. This doesn't mean all our measurements are wrong, but it means they might have direction-dependent corrections we haven't applied. The next generation of observatories will push our understanding of the axis of evil to new limits. Multiple missions are in development or planning stages that could finally resolve whether these anomalies are real or artifacts. Let's explore what's coming and what it might reveal. The Simons Observatory, currently being built in Chile's Atacama Desert, will observe the cosmic microwave background with unprecedented sensitivity using advanced superconducting detectors cooled to near absolute zero. It will map the polarization of the cosmic microwave background with exquisite detail. Polarization holds information that pure temperature measurements miss, potentially revealing whether the axis of evil extends to polarization patterns. If it does, that would be powerful evidence for real cosmic anisotropy rather than instrumental artifact. The CMBS-4 experiment, a proposed next generation ground-based observatory, would take this even further. With tens of thousands of detectors operating simultaneously, it would map the entire sky with sensitivity far exceeding anything we have today. More importantly, it would observe over multiple years, allowing researchers to identify and remove foreground contamination with unprecedented accuracy. Any systematic errors from our galaxy or solar system should be clearly separable from truly cosmic signals. If the axis of evil survives CMBS-4's scrutiny, few would doubt its reality. Space missions are also in development. The Lightbird satellite, planned by Japanese space agency JAXA for launch in the late 2020s, will focus on polarization measurements to search for primordial gravitational waves from inflation. But in doing so, it will also provide independent verification of large-scale anomalies. Its orbit and instrumental design are completely different from Planck, eliminating whole classes of systematic errors. Perhaps most intriguing is the PICO mission concept being studied by NASA. PICO, the probe of inflation and cosmic origins, would be specifically designed to answer fundamental questions about the early universe, including the reality of large-scale anomalies with sensitivity potentially 1,000 times better than Planck for certain measurements. PICO could detect directional effects that are currently just below our detection threshold. It could map how cosmic expansion varies with direction, test whether fundamental constants differ across the sky, and search for signatures of cosmic topology or multiverse collisions. The data from these missions won't arrive all at once. Science is a process of gradual refinement, each experiment narrowing the uncertainties and pointing toward the next question. But within the next decade or two, we should know definitively whether the axis of evil is real physics or a measurement artifact that finally got pinned down and explained. Beyond electromagnetic observations, gravitational wave astronomy offers a completely independent probe of cosmic structure. As LIGO, Virgo, and future detectors like LISA observe gravitational waves from colliding black holes and neutron stars across the universe, we'll build up a map of events in spacetime. If the universe has directional properties, They might show up in the distribution or properties of gravitational wave sources. Perhaps black holes form preferentially in certain orientations. Perhaps gravitational waves propagate slightly differently in different directions, arriving with subtle timing or polarization differences that reveal anisotropy. This is speculative, but it's testable. The gravitational wave background, the combined hum of countless unresolved sources across cosmic history, might carry imprints of large-scale structure that complement what we see in the cosmic microwave background. Neutrino astronomy represents another frontier. Neutrinos barely interact with matter, traveling through the universe essentially undisturbed since their creation. A cosmic neutrino background exists, analogous to the cosmic microwave background, but from even earlier in the universe's history. We haven't detected it yet. Neutrinos are notoriously difficult to catch, but future detectors might succeed, giving us a view of the universe from when it was just 1 second old. If that neutrino background shows directional patterns matching the axis of evil, it would prove the anisotropy existed from the earliest moments, ruling out many late-time explanations. Large-scale structure surveys are rapidly expanding our 3D map of the universe. Projects like the Dark Energy Spectroscopic Instrument, DESI, are measuring the positions and distances of tens of millions of galaxies. This creates a detailed map of cosmic structure that can be compared to predictions from isotropic models. Already, DESI has found hints of variations in cosmic expansion at different epochs. As the dataset grows, researchers will test whether structure formation proceeded uniformly in all directions, or whether directional biases exist. They'll look for correlations between the cosmic web's orientation and the axis of evil. If galaxies preferentially align along that axis, or if voids and filaments show directional dependencies, it would be powerful evidence that something truly cosmic is going on. The Vera Rubin Observatory, beginning operations soon, will photograph the entire visible sky every few nights for a decade. This will create an unprecedented time-lapse movie of the universe, tracking how billions of galaxies move and evolve hidden. In that data might be directional effects we've never been able to detect. Perhaps dark energy's acceleration varies slightly with direction, causing galaxies in different parts of the sky to accelerate at different rates. Perhaps the cosmic web's growth shows asymmetries over time. The statistical power of having billions of galaxies to analyze means even tiny directional effects should become detectable if they exist. Beyond observational missions, theoretical work continues at full intensity. Researchers are developing new statistical tests specifically designed to detect anisotropy, while accounting for all possible sources of contamination and systematic error. They're creating more sophisticated simulations that include every known foreground effect, testing whether the combination of all these effects could somehow conspire to create false patterns that look like the axis of evil. Machine learning is being applied to the problem, training neural networks on simulated cosmic microwave background data to identify subtle patterns that human-designed statistics might miss. These AI systems might find correlations or features we never thought to look for, potentially solving the mystery by revealing hidden structure in the data. Some of the most exciting theoretical work involves quantum cosmology. As researchers develop better theories of quantum gravity, they can make increasingly specific predictions about what signatures the Planck epoch should leave in the cosmic microwave background. String theory, loop quantum gravity, causal set theory. Each approach makes different predictions about large-scale structure and potential anisotropies. As observations improve, we might be able to use the axis of evil and related anomalies to test these theories of quantum gravity. This would be remarkable, using observations of the largest structures in the universe to probe physics at the smallest possible scales. The possibility of detecting the cosmic gravitational wave background from inflation is especially exciting. Inflation should have created gravitational waves that stretched to cosmic scales, leaving a specific pattern in the polarization of the cosmic microwave background called B modes. Multiple experiments are searching for these B modes. If found, the pattern of B modes across the sky will reveal information about inflation's properties, and if B modes show alignments or directional patterns, it would prove that inflation itself was anisotropic, directly linking the axis of evil to the earliest moments of cosmic history. This would revolutionize our understanding of inflation, requiring entirely new classes of models that can generate both the rapid expansion we know happened and the directional properties we observe. Some researchers are thinking even more radically. What if the anomalies we're seeing are actually signals from before the Big Bang? Certain cosmological models, like conformal cyclic cosmology proposed by Roger Penrose, suggest the universe undergoes infinite cycles of expansion and rebirth. In these models, structures from a previous cosmic cycle could leave imprints that survive through the Big Bang into our current universe. The axis of evil might be such an imprint, a fossil from a previous iteration of reality. This is highly speculative, but is testable. Different pre-Big Bang models predict different patterns of anomalies. As our maps of the cosmic microwave background improve, we can compare them to these predictions. The role of dark matter in these anomalies deserves deeper exploration. We know dark matter exists from its gravitational effects, but we don't know what it is. Could dark matter have properties that create directional effects? Perhaps dark matter particles have preferred directions of motion or alignment that we haven't detected in local measurements but show up in cosmic averages. Some exotic dark matter models predict interactions with ordinary matter that vary with direction or create anisotropic distributions on large scales. The direct detection experiments searching for dark matter particles might need to consider whether their results depend on which direction in space Earth is moving at any given time. If dark matter has directional properties aligned with the axis of evil, laboratory experiments might show seasonal variations or daily variations as Earth rotates and orbits, changing its orientation relative to the cosmic axis. Behind every scientific discovery are human beings. Brilliant, flawed, passionate people driven by curiosity and sometimes ego. The story of the axis of evil is also a story of scientific culture, of how researchers react when confronted with data that challenges everything they built their careers on. Kate Land was a postdoctoral researcher when she started analyzing WMAP data. Young scientists in her position face enormous pressure. They need publications to get permanent positions. They need to prove themselves to established researchers. But they also have less to lose than senior scientists who have invested decades in the standard model. When Land and her collaborator João Maguejo found the quadrupole-octupole alignment, they faced a choice. They could downplay it, noting it as a curiosity and moving on to safer research, or they could make it central to their work, knowing it would be controversial and that many colleagues would dismiss it as error or inexperience. They chose to pursue it, publishing papers that openly challenged the cosmological principle. The reaction was swift. Some senior cosmologists were encouraging, appreciating that good science requires questioning assumptions. Others were hostile, viewing the claims as sensationalist or insufficiently rigorous. Land gave talks at conferences where her results were picked apart, criticized, and sometimes dismissed before she could fully explain them. This is how science works, through vigorous debate and criticism. but it's also grueling on a personal level. Imagine presenting research that suggests everyone's been wrong, that the foundation of an entire field needs re-examination, and having a room full of experts tell you why you're mistaken. Most scientists would retreat. Lan persisted. She refined her analyses, addressed criticisms, and collaborated with other researchers to verify the results independently. Her persistence paid off when Planck confirmed the anomalies. João Magalhães, her collaborator, was already a controversial figure in cosmology. He had previously proposed varying speed of light theories, suggesting that the speed of light might have been different in the early universe. This is heretical in physics. The constancy of light speed is built into special relativity's foundation. Magalhães argued that allowing light speed to vary could solve certain cosmological problems without invoking inflation. The physics community was divided, with most researchers skeptical, but a minority intrigued. So when Magalhães co-authored papers on the axis of evil, some colleagues were predisposed to skepticism. He had a reputation as a maverick, someone willing to challenge sacred cows. This can be valuable in science. Progress requires people willing to think outside conventional frameworks, but it also means ideas get associated with personalities, and scientific judgment can be clouded by personal reactions to the messenger rather than the message. The Planck team faced their own challenges when their data confirmed the anomalies. They had spent years building the most sophisticated cosmic microwave background observatory ever. Their mission was to precisely measure the parameters of standard cosmology, nailing down the universe's age, composition, and geometry. Finding anomalies that challenged the standard model was not what they expected or wanted. The team included hundreds of scientists from dozens of institutions. Reaching consensus on how to interpret and present controversial results was difficult. Some team members argued for emphasizing the anomalies, noting their statistical significance and potential revolutionary implications. Others argued for caution, pointing out that the significance levels weren't overwhelming and that previous anomalies had often disappeared with better data or analysis. The compromise was to present the anomalies thoroughly in technical papers, while being carefully neutral in press releases and public statements. This caution is understandable, but frustrating. The public wants clear answers. Is the universe isotropic or not? Scientists know reality is more complex. Data has uncertainties. Statistical significance is a spectrum, not a binary. The Planck team couldn't definitively say the cosmological principle is wrong, because the evidence, while suggestive, wasn't conclusive beyond all doubt. But they also couldn't say everything is fine, because the anomalies were persistent and significant. So they said, essentially, we found these interesting patterns that might be real or might be statistical flukes, or might indicate physics we don't understand, and more research is needed. This is honest and accurate but unsatisfying. It leaves the mystery hanging, unresolved. The media coverage of the axis of evil illustrates the challenges of science communication. When the initial results were published, some news outlets ran headlines like, "Universe has mysterious axis that threatens cosmology." These are accurate in a sense, but sensationalized. Other outlets went with "Scientists find pattern in cosmic background radiation," which is accurate but downplays the significance. The truth is that most people, even educated people interested in science, don't have the background to evaluate statistical significance or understand what a 2 to 3 sigma result means. They want to know, should this change how I think about the universe? And scientists struggle to answer that because they don't know yet themselves. This creates a gap where speculation and misunderstanding can flourish. Some popular accounts of the axis of evil veer into pseudoscience, claiming it proves astrology or mysticism, or that the universe was designed with Earth in mind. These claims are nonsense, but they exploit the legitimate uncertainty in the scientific community. When scientists say, "We don't fully understand this," some people hear anything is possible, including my favorite unscientific belief. The scientific community's response to this misappropriation is often to downplay the anomalies publicly, emphasizing that they're probably nothing, while privately continuing to study them intensely. This protects against pseudoscience, but also undersells the genuine mystery. Within the cosmology community, the axis of evil has created some interesting fault lines. Older researchers, those who built their careers on the Standard Model, tend towards skepticism. They've seen anomalies come and go. They remember when other crisis in cosmology moments turned out to be measurement errors or misunderstandings. They have hard-won intuition that most surprising results disappear with better data. Younger researchers, especially those who came of age after WMAP and Planck, are more open to the possibility that the anomalies are real. They don't have the same emotional investment in the Standard Model. They're excited by the possibility of being part of a paradigm shift, of seeing cosmology transform during their careers. This generational divide isn't absolute. Plenty of young researchers are skeptical and senior researchers are intrigued. But there's a pattern, and it influences how the field approaches the problem. The sociology of science plays a role too. Research funding tends to go toward projects that build on established success, rather than those that challenge foundations. If you propose an experiment to measure cosmic microwave background parameters more precisely within the Standard Model, you're likely to get funded. If you propose an experiment specifically to test whether the cosmological principle is wrong, you're taking a risk. Your proposal might be seen as speculative or unlikely to produce results. This creates a conservative bias in what gets studied, even though revolutions in understanding come from challenging established ideas. Some researchers have built careers around the axis of evil, becoming specialists in large-scale anomalies and anisotropic cosmology. This is risky career-wise. If the anomalies turn out to be artifacts, these researchers might be seen as having wasted years pursuing a dead end. But if the anomalies are real, they'll be pioneers, remembered as the people who recognized the significance when others dismissed it. The personal stories of these researchers are fascinating. Many have described moments of doubt, wondering if they're chasing ghosts or making fundamental mistakes. The lonely feeling of working on a problem most colleagues consider unimportant or already solved. The thrill when a new analysis confirms what previous work suggested. The frustration when critics misunderstand or misrepresent their findings. Science is often portrayed as purely objective, data-driven, free from human emotion. But scientists are human. They have intuitions, biases, hopes, fears. They want to be right. They want recognition. They want to discover something important. These motivations can drive excellent work, but they can also lead researchers astray, seeing patterns they want to see, or dismissing evidence they find uncomfortable. The peer review process is supposed to catch these errors, but peer review is also done by humans with their own biases. The result is that science progresses unevenly, with some ideas getting more scrutiny than others based on who proposes them and how they fit existing paradigms. The axis of evil doesn't exist in isolation. Across astrophysics, there are numerous observations that don't quite fit standard models, each potentially related to the others in ways we don't yet understand. Let's explore this constellation of cosmic mysteries and see if patterns emerge. The Hercules Corona Borealis Great Wall is a structure so large it shouldn't exist. This apparent galaxy filament stretches across 10 billion light-years, making it the largest known structure in the universe. According to standard cosmology, there hasn't been enough time since the Big Bang for gravity to assemble something this large structures form hierarchically, with small objects merging into larger ones over time. But the universe is only 13.8 billion years old, and simulations suggest structures larger than about 1.2 billion light-years shouldn't have had time to form. Yet here's something 8 times larger. Is this connected to the axis of evil? Perhaps large-scale directional properties in the universe allow faster structure formation along certain axes, or perhaps the cosmic web has intrinsic large-scale organization we haven't accounted for in our models. The Shapley concentration, a massive supercluster of galaxies, creates another puzzle. Our local group of galaxies, including the Milky Way, is moving toward the Shapley concentration at high speed, pulled by its enormous gravitational attraction. But when astronomers calculate the mass needed to explain our motion, they consistently find that there's not enough visible or even dark matter in that direction to account for it. Something is pulling us, something with enormous mass, but we can't see it. Some researchers propose a dark flow, a systematic motion of galaxy clusters toward a particular region of space, potentially indicating enormous structures beyond the observable universe pulling on everything we can see. These claims are controversial, with different research teams getting different results. But if confirmed, dark flow would be direct evidence that the observable universe is part of something larger, and that our universe's contents are being influenced by mass distributions we cannot directly observe. The void problem adds another wrinkle. Cosmic voids, the huge underdense regions between galaxy filaments, are larger and emptier than standard structure formation should produce. The largest voids span hundreds of millions of light-years and contain very few galaxies. Why did matter avoid these regions so thoroughly? Some researchers suggest the voids are too well defined, with edges that are too sharp, as if something carved them out rather than letting them form naturally through gravity's subtle push and pull over billions of years. Could voids be related to directional properties in dark energy or modified gravity? If the forces driving cosmic acceleration vary with direction or location, they might create asymmetric void structures. The Eridanus supervoid, positioned roughly in the direction of the cold spot in the cosmic microwave background, has been studied intensively as a potential explanation for that anomaly, but as mentioned earlier, it's too small to fully explain the cold spot's properties. Yet its existence there, aligned with an anomaly, suggests possible connections. The distribution of satellite galaxies around large galaxies presents another mystery. The Milky Way has dozens of satellite galaxies orbiting it. These satellites aren't randomly distributed. They tend to lie in a thin plane, like planets in a solar system. The Andromeda Galaxy satellites show similar planar distributions. This is unexpected. Satellites should be captured from all directions over time, creating a roughly spherical distribution. Instead, we see organization, planes of satellites that rotate coherently. The planes around the Milky Way and Andromeda are roughly aligned with each other and with the larger cosmic web. This suggests that galaxy formation and the capture of satellites is influenced by large-scale structure in ways current models don't fully capture. Could this be related to the axis of evil? If the universe has preferred directions, perhaps angular momentum gets imparted preferentially along those directions, causing rotating structures like galaxies and satellite planes to align with cosmic axes, the cosmic dipole. Our motion through the cosmic microwave background is well established. Earth, the Sun, and our entire galaxy are moving at about 370 kilometers per second relative to the cosmic microwave background rest frame. This motion creates a dipole pattern, with the microwave background appearing slightly hotter in the direction we're moving and cooler behind us. But here's the weird part. When astronomers measure our motion using other methods, like the distribution of radio galaxies or the motion of galaxy clusters, they sometimes get slightly different answers. The dipole seems to depend on what you're measuring. Everything should agree. There's only one motion. Yet different traces give results that differ by more than measurement uncertainty. This might indicate that the universe itself has large-scale bulk flows, or that our cosmic motion is more complex than a simple dipole suggests. Some researchers propose a quadrupole component to our motion, which would be evidence of anisotropic cosmic expansion, the universe accelerating differently in different directions, the distribution of active galactic nuclei, the brilliant cores of galaxies powered by supermassive black holes, shows unexpected patterns. When mapped across the sky, active galactic nuclei seem to have preferred directions at various distance scales. Their orientations, the angles of their jets and accretion disks, show alignments over distances of hundreds of millions of light years. There's no known mechanism for supermassive black holes separated by such vast distances to coordinate their spins. Yet the statistical signal is there in multiple surveys. Some researchers suggest this alignment is caused by primordial vorticity, swirling motions imparted to matter in the early universe that influenced how structures formed and how black holes acquired their angular momentum. If true, it would mean the universe had rotation or vorticity on scales much larger than previously suspected, potentially connecting to the axis of evil. The cosmic optical background, light from all the stars and galaxies throughout cosmic history, should be isotropic. When we subtract known sources, what remains should be uniform across the sky. It isn't. There are directional variations that exceed what foreground contamination can explain. Something is making the universe's integrated light output vary with direction. Are we seeing the effects of truly cosmic scale structure? Galaxy superclusters and voids so large, they create measurable variations in the sky's brightness. Or is this another manifestation of anisotropy built into the universe's structure? The high-energy cosmic ray spectrum presents its own mysteries. Cosmic rays are particles, mostly protons, accelerated to enormous energies by violent cosmic processes. The highest energy cosmic rays have energies that shouldn't be possible. They're so energetic that they should interact with the cosmic microwave background during their journey to Earth, losing energy through a process called the GZK cutoff. This limits how far the highest energy cosmic rays can travel, creating a sphere around Earth beyond which we shouldn't detect them. But we do detect ultra-high energy cosmic rays that seem to violate this limit. Moreover, these ultra-high energy cosmic rays don't arrive uniformly from all directions. There are hot spots and cold spots, directions from which more or fewer arrive than expected. Some of these directions correlate with nearby galaxies or large-scale structures, suggesting local sources. But others don't correlate with anything obvious, hinting at unknown sources or processes. Could ultra-high energy cosmic rays be preferentially accelerated or propagated along certain cosmic directions? If the universe has large-scale magnetic fields aligned with structural axes, they could channel cosmic rays, creating the observed patterns. The fast radio burst phenomenon adds contemporary mystery to this list. These are brief, intense pulses of radio waves coming from distant galaxies. We've detected hundreds now. but we still don't fully understand what produces them. Neutron stars with extreme magnetic fields are the leading candidate, but the details remain unclear. Intriguingly, when researchers map fast radio bursts on the sky, hints of non-random distributions emerge. Too few for strong statistical claims, but suggestive. As more are detected, we'll see if they're truly uniform or if there are preferred directions, potentially indicating that whatever produces them is influenced by a large-scale cosmic structure. The Lyman alpha forest, a series of absorption lines in the spectra of distant quasars caused by intervening hydrogen clouds, provides another probe of cosmic structure. These clouds trace the cosmic web's filaments and voids. When researchers analyze the three-dimensional distribution of Lyman alpha forest features, they find that structure formation matches predictions well on small and medium scales, but shows subtle discrepancies on the larger scales. The universe seems slightly more homogeneous on very large scales than simulations predict, echoing the missing large-scale power problem in the cosmic microwave background. Are we seeing different manifestations of the same underlying issue? Perhaps the universe's initial conditions weren't perfectly random, or inflation didn't operate quite as standard models assume, leaving imprints across multiple observational windows. So where does this leave us? After exploring the axis of evil from every angle, the observations, the theories, the implications, the human drama, the philosophical meaning, what can we conclude? Honestly, not much with certainty. And maybe that's the point. The universe is under no obligation to make sense to us. It doesn't owe us clear answers or satisfying explanations. It simply exists, vast and strange and beautiful, waiting for us to ask better questions and build better instruments and think more carefully about what we observe. The axis of evil is a signpost pointing toward something. Maybe it points toward real cosmic anisotropy, a universe with structure and direction beyond what our theories predicted. Maybe it points toward subtle measurement systematics we haven't fully understood despite years of effort. Maybe it points toward new physics lurking in the gap between quantum mechanics and general relativity. Or maybe it points toward the limits of knowledge, the boundary where observation becomes too uncertain and interpretation too ambiguous to support definite conclusions. Whatever the axis of evil ultimately teaches us, the journey of discovery is valuable regardless of destination. Every paper published, every analysis performed, every debate held, every instrument built contributes to human knowledge and capability. Even if this particular mystery never resolves, the infrastructure of understanding we build while pursuing it enables future discoveries. Science is cumulative. Nothing is wasted. As new telescopes come online and new data accumulates, the picture will clarify. Maybe slowly, frustratingly slowly, but progressively. Perhaps within a decade, we'll have definitive answers. Perhaps it will take a century. Perhaps the answer will come from an unexpected direction, a theoretical breakthrough or observational discovery that suddenly makes everything clear. Or perhaps the axis of evil will remain a footnote, a curious anomaly that never quite resolved, a reminder of how much we still don't know. For anyone fascinated by this mystery, by the possibility that the universe harbors secrets that challenge everything we thought we knew, the best response is patience mixed with passionate curiosity. Follow the research. Read the papers. Watch as new observations are announced and analyzed. Support science education and funding so future generations can continue this work and maintain a sense of wonder. In a universe containing hundreds of billions of galaxies, each with billions of stars across spans of space and time that dwarf human comprehension, finding patterns that shouldn't exist reminds us how much remains to discover. We're explorers standing at the shore of an infinite ocean, having learned to sail but still mostly ignorant of what lies beyond the horizon. The axis of evil might be a distant island just coming into view, or it might be a mirage, or it might be something we lack concepts to properly describe. The cosmos is not silent. It speaks to us in the language of light and gravity, particles and fields, patterns and anomalies. When we listen carefully, when we build instruments sensitive enough and theories sophisticated enough, we hear whispers of truths that transform understanding. The axis of evil is such a whisper, faint and ambiguous, but potentially profound. Will it lead to revolution? Will it reshape cosmology and force textbook rewrites? Will it stand as one of the great discoveries of the 21st century? Or will it be explained away, relegated to historical footnotes about measurement challenges in early cosmic microwave background experiments? We don't know. And that uncertainty, that openness to possibilities, that acknowledgement of how much remains mysterious, is what makes science and exploration and human curiosity so worthwhile. The universe has a secret. Maybe we'll figure it out, maybe we won't, but we'll keep trying, keep observing, keep thinking, keep questioning, because that's what we do. That's what makes us human. The axis of evil awaits, the universe awaits, and somewhere out there in the cosmic dark, answers are waiting to be found, or questions we haven't yet learned to ask. Either way, the journey continues, and that, ultimately, is the most important thing. Not the destination, but the journey. Not the answers, but the questions. Not certainty, but the passionate pursuit of understanding, despite knowing we might never fully succeed. If you've made it this far in this exploration, thank you for joining me on this journey through one of cosmology's deepest mysteries. Keep looking up, keep questioning, keep wondering. The universe is stranger than we imagine, and possibly stranger than we can imagine. But that's what makes it worth studying, worth contemplating, worth devoting our brief moments of consciousness to trying to understand. The axis of evil might be the key to everything, or it might be nothing. But the only way to find out is to keep searching, keep observing, keep thinking. And that search, that fundamental human drive to understand our place in the cosmos, is beautiful in itself, regardless of what we ultimately discover.